All right, so next up we're going to go ahead and look at periodic functions. And so I think that I would have given you this formula previously and sort of told you, don't worry about it, you're not going to need it. And there's going to be a like recall right here where I write down that same definition. If you already have it, just like hold on for a second and then catch up with me in when I'm done with it. So if f of t is periodic with period t, and it's piecewise continuous, and you can take Laplace transforms of f, then we have this property that L of f, which would normally be sort of that infinite integral that we learned for Laplace transforms, can be computed as a finite integral where you only integrate over the period once, and it's just the regular definition of a Laplace transform over that range, and we just add this extra factor out front to account for the fact that we integrate over the period instead of the full domain of the function. And even though I'm not going to ask you to know this fact and memorize it because it's a little bit confusing, I think, I thought it would be good to still do an example because this section is a little bit shorter, so we have time for it. So this is prob 4.4.8. And when I say periodic, we're thinking about things that repeat. So here's like a picture of the function we're thinking about. All of t, there's some e right here, and we're going to find L of e. Wondering what that is. And the way e behaves is it starts off at 1, and then at 1, it drops down to 0. At 2, it bumps back up to 1. At 3, it goes back down to 0. And it just repeats that. And I'll stop drawing it once I run out of room on the line. So that's sort of what we're thinking about right here. And we need to find L of e. And the first thing that we need in order to do this is to sort of identify how e fits into this property that we just learned. So let's think about the behavior of e. The period of e is sort of the time interval over which you could record its behavior once and then just copy paste it forever. And so that's going to be this window right here. Sort of if I make all my cuts at 2, 4, 6, all the even numbers, then my picture of e is always the same. So I know that right here is a period, and that period length is 2. And that's a period, and that's a period as well. So it has period t equals 2. That's the first thing that I need in order to use my property. The other thing I need is to sort of know how to represent e and its behavior as a function. So between, let's say 0 less than or equal to t less than or equal to big T, the period, e is going to act like, I'm going to call the function e tilde, I guess, just to avoid any confusion. But what it does is it starts off as valued 1, and it does that for t up to 1. And then it turns to 0, 1 less than t less than 2. And then since t is, or capital T is 2, that's all we need. So from here we have all the little pieces we need in order to apply our new property for how to take a Laplace transform of a periodic function. So L of E is 1 over 1 minus e to the minus st, integral 0 to t, e to the minus st, this e tilde of t with respect to t. Lots of t's hanging around. I'm going to go ahead and replace the capital T right now. 1 minus e to the minus 2s, integral from 0 to 2. E to the minus s, that's a little t, it stays the same. E tilde of little t, that stays the same, integrated with respect to t. And I don't think I can finish out this integral on this page, so I will go ahead and continue it right here. That way things don't get to be too cramped. So I'm looking at L of E. I said, it's kind of a curly bracket, looked like 1 over e to the minus 2s, integral 0 to 2, e to the minus st, e of t integrated with respect to t. And our e of t, remember, is something that's 1 and then 0, switching out 1. Oops. So our 1 over e to the minus 2s is times this integral of a piecewise function. Anytime we work with piecewise functions, we break it up into two pieces. So we think about e to the minus st times e evaluated from 0 to 1, plus e to the minus st times e evaluated from 1 to 2. And between 0 and 1, e is 1. Shouldn't have done that. Between 1 and 2, e is 0. So I've just got 1 over e to the minus 2s, integral 0 to 1, e to the minus st, integrated with respect to t, because the second integral will just become 0. So that's going to give me 1 over e to the minus 2s times minus 1 over s. There's a negative s times my e to the minus st, and I'm integrating with respect to t. E to the minus st going from t equals 0 to t equals 1. 1 over e to the minus 2s minus 1 over s times e to the minus s minus e to the minus s times 0. So 1 over e to the minus 2s times negative e to the minus s over s plus e to the minus s times 0 is just 1, so 1 over s. So I guess we could pull out that common 1 over s, and then we're just looking at let's see, 1 minus e to the minus s, all divided by e to the minus 2s. And maybe you could simplify that further, but I'm going to go ahead and say that that's good enough right there. And we have a little bit of time before this video is too long, so I just want to stop real quick. This was kind of a long problem. You know, you have to identify the period, do this whole integral. There's making a piecewise integral. So by the time you get to this point right here, it would have been so easy to make the mistake that I start plugging in if I had like, oh, white will not show up here. If I had 1 over e to the minus 2s, I could have done like 1 over s e to the minus st evaluated from 0 to 1, and then 1 over e to the minus 2s minus 1 over s times e to the minus 1t minus e to the 0 times t, like that. Because a problem with these types of questions, as we saw in class last time we met, is that it's really easy to swap those variables. So again, that was the sort of place where that could go wrong. Just be careful that you don't do that. I'm erasing the note because I don't want somebody who's reading the notes to think that for some reason that was something that we should do. That was just a word of warning. So I'm going to go ahead and stop this video right here, and then we'll come together to talk about this in the next